Welcome to 3.2, which is on addition and subtraction. We're going to talk about several different ways on how you can add and subtract and show students how to do these operations. We're going to talk about using base 10 blocks and some number lines, lots of different strategies. So try to keep an open mind. Some of these strategies you might appreciate, and then some you might say, I might leave this one. It doesn't make sense to me, which is totally fine. But just keep in mind that, you're going to be working with a lot of different types of students. And I think it's important to be able to have, a big toolbox with lots of different methods available in case, the regular standard algorithm doesn't work for kids. So let's jump in and let's start with this example, 37 plus 78, and we're going to do this example with base 10 blocks. So just to review from last time, I'm actually going to show you a picture here. This is what real base 10 blocks look like. You should have a set of these hopefully in your classroom. A lot of elementary school classrooms do. And the small little cubes at the bottom, so these would be the units. So those each stand for 1. These sticks, these are called longs, and there's 10 units in those, so these are 10. These flat pieces here, these are called flats, and those are 100. And then this is the cube, which is 1,000. So 1, 10, 100, 1,000. Okay, so those are the actual blocks, but then we're going to draw pictures of blocks, which is helpful because elementary school students are going to draw pictures of them too. So they're not always going to be working with the blocks. So there's many worksheets that ask them to draw blocks. I know my kids, when they take their homework, when they do their homework at home, they're constantly drawing pictures of base blocks on their paper because, it really resonates with them and helps them add. So just to recap, so if we're drawing it flat on a piece of paper, I'm going to do a dot for a unit, and that's worth 1. I'm going to do a stick. We'll call that a long, and that's worth 10. And then a square is going to be, that's called a flat, and that stands for 100. So if I'm adding 37 plus 78, I'm going to draw 37. So 10, 20, 30. 1, 2, 3, 4, 5, 6, 7. 78 is going to be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I'm going to count them all together because that's what adding is. We're going to group them together. But you'll see here, so if we look at our units, I've got 15 units there. So the problem with that is if we say, okay, well, we've got 15 ones, or units, and then we have, let's see, we've got 10 tens. Okay, what does that mean in terms of the answer? Well, if you have 10 tens, that's 100, and 15 ones is 15, so you get 115. Okay, so that's one way to do it. Visually though, and for kids, this would be so much easier. Instead of thinking about it that way, what we can do is we can just regroup them. So we know that a long is worth 10. So if I count 10 units, okay, and I'm going to just use a different color for this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to circle a group of 10, and I'm going to cross this off, and then I'm going to make a long out of it. Okay, 10 units are the same thing as 1 long. And then I'm going to do the same thing with longs. So I'm going to circle 10 longs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we've got 10 longs here. And I'm going to cross that off. 10 longs is equal to a flat. 10 tens is 100. Okay. And then I'm going to ask myself, well, what do I have left? So once I'm done regrouping and I can't do any more groups of 10, I'm done regrouping, then I ask what's left. So what is the answer? And a lot of times when kids do this, they'll actually have like a sheet of paper and it'll be labeled flat, long, unit. So what's my total? I have 1 flat left over, which is right here. I've got 1 long left over, and then I've got 1, 2, 3, 4, 5 units left over. So my answer is 115. And you may be thinking, well, gosh, that took a lot of work. I could have just done it using the standard algorithm by putting them on top of each other and carrying and getting 115. Yes, that is faster. And eventually that's where we want students to go because it is more efficient. But our goal here is for deep understanding. And I'm sure you've done this you know, hundreds of times where you add and you carry, but do you think about what that carrying actually means? So when you write down the 5 and carry the 1, are you actually conceptually understanding what you're doing, or are you just going through a rote set of steps? And it's okay to go through that rote set of steps as long as you have that understanding to begin with. So, and I will tell you from a kid's perspective, when they're not even introduced to that quick algorithm, well, and even if they are, a lot of times they'll end up choosing this picture method just because it makes sense to them. So let's try the second example. So this would be a good place to pause the video and try it on your own. So I'm going to draw 156. So 100, 10, 20, 30, 40, 50, 2, 3, 4, 5, 6. So 156 and then 85. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. I'm going to start with my ones and I'm going to regroup. So 5, 6, and you know what? I'll grab a different color real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 there. And I make a long out of that. And then I'm going to count my longs and see if I have a group of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I do. So I'm going to cross those off and I'm going to make a flat. And then once I'm all done, I'm going to jot down, well, what are my totals? So I have 2 flats. I've got 1, 2, 3, 4 longs. And it looks like I have 1 unit left over. 241. And certainly when you're done, I mean, it's definitely helpful to, you know, add with that standard algorithm just to make sure, you know, you get the right answer. But the goal here is the process and the picture, not the 241. Okay, so let's jump ahead. So the other way that we could visualize adding is with a number line. So for example, this picture right here starting at 0 shows we're jumping to 3 and we're jumping to 4. So 3 plus 4 is equal to 7. It shows that. So let's see if we can figure out what this next picture represents. So this top one, we start at 0 and we jump to 5, and then we're jumping 2 more and we're landing at 7. We start at 0 and we go to 2, and then we jump 5 more and we get 7. So it's showing either way, 5 plus 2 or 2 plus 5, we both equal 7. And with kids, it's fun to talk about when you're doing number lines, you can talk about this in terms of hops. So I've seen lots of cute worksheets with like frogs where, you know, you're starting at a number and you're hopping forwards or backwards. And just that change of wording, using that word hop sometimes can resonate well with kids. Okay, so I mentioned the word algorithm just a minute ago, but let's talk about what is an algorithm. So I mentioned the standard algorithm for adding. So standard algorithm is when, you know, for example, if you're adding these two numbers, you're starting with the 5 and the 7, you're adding them. 5 plus 7 equals 12. So you put down the 2, you carry the 1. 1 plus 1 is 2, plus 2 is 4. So this is the standard addition algorithm. Algorithm meaning just a procedure. Well, there's some other algorithms that we can use. So we're not going to use pictures, but there's some other algorithms besides just the standard one that can be helpful. So the first one is called partial sums algorithm. So there are 2 ways to write it. On the left here, I'm going to say option 1. This is my preference out of the 2. So 345 plus 278. The partial sums algorithm, and when you do this with kids, actually, it's kind of nice even if you have like a grid or grid paper. You could do centimeter paper for this just to kind of line everything up. So you start with the 5 and the 8 and you add the 5 plus 8 and you get 13. So you actually just write down 13. You don't carry anything. And then you add the 4 plus 7 and you get 11. You write that down below, just like you would the number 11. And then you add the 3 plus 2 and you get 5. So essentially it's a lot like when we carry, it's just we're writing everything down below in the category or in the column that it belongs. Okay, then we add everything up. So the 3 comes down 1 plus 1 is 2, and 5 plus 1 is 6, and we get 623. And again, the goal is not the 623 part. It's the knowing how to do it with the partial sums algorithm. Okay, so the other way is to write it down in words. So you could say, I'm going to give myself some more room here. The downside to this is it's definitely more writing. So you could say 300 plus 4 tens plus 5 ones plus 200, 7 tens, 8 ones. And then we're going to add these together. So if we have 5 plus 8, that gives us 13 ones. 7 and 4 is 11 tens. 3 plus 2 is 5 hundreds. Now, you could certainly at this point, if you wanted to draw a picture with the blocks, you could do that, or we could just think about it. Well, if 10 ones equals 110, then if we have 13 ones, then that means, okay, well, we've got a 10. So we're going to add a 10 over here, and that gives us 3 ones left over. And then 11 and 1 is 12 tens, okay? We know that 10 tens equals 100. So let's add another 100 over here, and we'll take off 10. So 10 tens is 100. So we put 100 in that left category, and we're left with 2 tens. 5 and 1 is 6 hundreds. So we're left with 6 hundreds, 2 tens, 3 ones, so 623, same answer. Okay. This one definitely, I don't prefer that one as much. It's a lot of writing. I think it's a lot of writing with kids, but just, you know, it's good to see some other options. Okay, and then the last one we're going to do, and then we're just going to do some practice, is left to right addition. Okay, so 897,537. Usually we work right to left, but it is possible. Some kids and some people's brains just work better going left to right, and it is possible to do left to right. So what you do is you start on the left. So 8 plus 5 is 13. And you're going to write 13 so that the 3 is in line with the 8 and the 5. And then the 9 and the 3, okay, you're going to add those. So 9 plus 3 is 12. Now, you could, if you wanted to, write it so that it's like this, okay? That would be, I think, a little bit simpler for kids. You could also, just to give you another option, put the 2 here and cross that off, and we're going to add a 1 and make this a 4. I think whenever you're crossing stuff off, though, I think it becomes a little bit more confusing. So I'm going to actually do it where I do 9 plus 3 is 12, and I write it down below here. And then 7 and 7 is 14, and I'm going to write it like that. And just like above, if we have these columns here, that makes things a little bit easier, and I definitely provide that for kids if I was doing this in elementary school. So now we're going to bring everything down. So we've got a 3, 3 plus 1 is 4, and then bring down the 1, and we're left with 1434 as our answer. So if you don't prefer this method, totally fine. We're just, you know, this is all about exposure, so we can see how to do things different ways. Okay, so example 6, you've got some practice there, so this would be a great time. Pause the video and try these, and I'll work these out right now. So 694, 539, and we're going to do partial sums. So I'm going to make some columns. So 9 plus 4 is 13, and I'm going to write that down like that. 9 plus 3 is 12, and 6 plus 5 is 11. Okay, now I bring everything down, adding if there's more than one number there. So 3, 1 plus 2 is 3, 1 plus 1 is 2, and carry down the 1. So I'm left with 1,233 as my answer. Okay, the other way to do it is write it out. So I've got 6 hundreds, 9 tens, 4 ones. I've got 5 hundreds, 3 tens, and 9 ones. So if I add all those together, so it means I have 11 ones, I have 12 tens, and I have 11 hundreds. So now I need to regroup. So 10 ones is a 10. So I'm just going to add another 10 over here to make, and I'm left with 1, 1 over here. 10 tens is 100. So I'm going to take off 10 here and put a 1 over here. So that leaves me with 12 hundreds. And then I know that, not 12, I know that 10 hundreds equals 1,000. So I'm going to take off the 10 there, gives me 2 hundreds, and that would give me 1,000. So 1,230. Whoops, you know what? I did that wrong. I said 9 plus 4 is 11. It is not. Ah, this is where it's good to check your work. 9 plus 4 is 13 ones. Okay, so if I take off a 10 there, then I'm left with 3 left over. Okay, cool. So we've got 1, 2, 3, 3, 1,233. Awesome. We got the same answer as before. Okay, so last but not least, we're going to do left to right. So 6, 9, 4, 5, 3, 9, and I'm going to draw some columns. So I'm going to start with the 6 and the 5 is 11. The 9 plus 3 is 12. And then 9 and the 4, I'm going to get this right this time, is 13. And then I'm going to add them all up. So carry down the 3. 2 plus 1 is 3. 1 plus 1 is 2. And then carry down that 1, and I'm left with the same answer as with the other ones. So which one did you like best? I'm curious to figure out what you all prefer. Okay, so let's talk about properties. So we're going to, throughout the class, we're going to talk about properties of different types of number systems. So some of this might be new right now. Some of it might review. You might remember some of this from elementary school, but by the end of the class, you'll see all of these properties quite a bit. So let's start with closure. So closure property just means when you do an operation, then you get the answer, or I'm sorry, let me start over. So when you do an operation, the answer that you get is the same type of number as the types of numbers that you use in the operation. So for properties of whole number addition, and let's actually review here. You know what, let me just scroll up real quick. Let's just review what a whole number is. So a whole number, 0, 1, 2, 3, 4, ... So whole numbers include 0 and any type of positive counting number. So when you add a whole number to a whole number, you always get a whole number. Is that true? Yes. Think about it. Is there any possible way to add two whole numbers and get a decimal or a fraction like 3/4? There's not. So that's called the closure property, when you're always going to get a whole number for an answer. So the commutative property, that just says that you can change the order when you add and you get the same answer. Now this doesn't work for every operation. So if we subtract two numbers and change the order, we're not going to get the same answer, but it does work for whole number addition. So for example, 5 plus 6 is the same thing as 6 plus 5. Now, to remember this property, when I was younger, I remember thinking about what it meant to commute someplace, like my commute to work. I get my car, I go to work, after work, I get my car and I come back. It's the same path, it's just a different order, and for some reason that helped me remember what it meant to what the commutative property meant. So we're just switching the order. The associative property has to do with parentheses, and I always think of the word, who do you associate with, or the phrase, and it could mean like groups of people. So associating with people, think of groups or parentheses. So it means that you can change the order of the parentheses and it doesn't change the answer. So you could have, notice that A, B, C, A, B, C. Numbers are in the same order. So numbers in same order. Parentheses are in different places. Okay, but we get same answer. So let's see if this works. I'm going to pick three numbers. So 4. Actually, you know what? Let's keep it easy. Let's do 1, 2, and 3. Plus equals 1 plus 2 plus 3. Let's put parentheses in different spots and see if we get the same answer. So the parentheses tell us to do that part first. So 1 plus 2 is 3, plus 3 is 6, And then 2 plus 3 is 5, so 1 plus 5 is also 6. So we get 6 equals 6, so it ends up working. And that will always hold true for whole number addition. And just like the last property, when you get into other operations like division or subtraction, it's not going to work. But we'll talk about that when we get there. So identity property, I want you to think of, the word identity. What does it mean to keep your identity? Well, if you keep your identity, it means that you very simply just kind of stay the same. You preserve yourself. Well, that's what it means in math. So an identity or an additive identity is the number that you can add to any number and it doesn't cause that number to change. And the additive identity for whole number addition is 0. So the additive identity for whole number addition is 0 because adding 0 to any whole number, well, in any number really, does not change its value. Okay. All right, so below is just a picture. This is a picture of an addition chart, and I just want to show you because this is interesting. Notice that the table is symmetric. So, and we might not be that surprised because if you think about it, like 3 plus 8, we get 11, is the same thing as 8 plus 3. And the same is true for any other box. So these two numbers are the same. Okay, 5 plus 1 is 6. 1, let's see, 5 plus 1 down here is 6. And so those are across from each other. So you notice the table is symmetric about the diagonal. And this shows the commutative property. It's a visual illustration of the commutative property in play with addition. All right, so the next part, let's talk about inequality of whole numbers. So we talked about properties and addition. This part isn't going to be too long, but let's just talk about the inequality symbols and what they mean and how we can talk about them. This part right here is kind of interesting. It's worth reading. It talks about the symbols less than and greater than. So let's just write that down. So less than, greater than, and where they originated from. So they were first used by the English astronomer and mathematician Thomas Harriot, and he came up with these. They have to do with they have to do with their relationship to the equal sign. So if we think about the equal sign and what it looks like, so this means that two numbers are equal. So for example, 3 equals 3. If you look at, I'm just going to get another color real quick. If you look at the distance between the two lines on either side, it's the same. So that's why, it's just an illustration that 3 is the same as 3 because the distance between those two bars on either side is the same. If you think about the less than and greater than symbols, for instance, so 3 is less than 4 or 5 is greater than 3. If you look at the distance between the two lines, so the distance over here between these two ends is greater than the distance on the left. So that's why that faces the greater of the two numbers. Or over here, this distance is greater than over here. So that distance, that side is facing the larger number. Okay, one more thing I want to mention. So I think usually it's really clear to people in elementary school students, that this symbol up here is less than and this symbol is greater than, but it's also important to be able to read those in opposite ways. So for example, this statement right here, you could read 3 is less than 4. You could also read it as 4 is greater than 3. Okay, so 3 is less than 4, 4 is greater than 3. It's important to note that because when you get to algebra, you'll see things like x is less than 6, or the x might be on the other side. So maybe it looks like this. And we don't ever want to say x is greater than 6 because that's a greater than sign. We would still say x is less than 6 regardless of which way you write it, because we talk about the x first, and we read the sign in the direction that it's headed. So if the x is on the smaller side of that sign, it's always less than. So I just wanted to mention that because sometimes that's a sticky area for students, especially in algebra and beyond. Okay, so let's talk about subtraction. So we talked about number lines and base blocks with addition, so let's do the same with subtraction. So let's look at these number lines. So one way to illustrate subtraction, we can start at 0, and if we want to do 7 minus 3, we could start at 7, and we could hop backwards 3, so the hopping backwards is your subtraction, and you're landing on 4. Okay, so this one right here, you could pause the video and try it on your own. So we're starting at 11, and then we're hopping backwards 3. So that's a minus 3. And then we're hopping backwards 1, 2, 3, 4, and we're landing at 4. So any hopping in the left direction stands for subtraction. And then with the base blocks, this is a little different than the addition. So with subtraction, what I usually like to do is I draw the first number only. I don't draw both numbers. I just draw the first number. And then I try to subtract, but if I can't, I'm going to make exchanges if necessary and take away the second number. Okay, so for this first example, 243, I'm going to draw 243. So 243. And next, I'm trying to take away 176. Okay, so let's start with the ones. So I'm trying to take away 6 ones, or 6 units. I don't have 6 units to take away. So what I'm going to do is I'm going to make an exchange. And what that means is I'm going to take one of these base 10 blocks here. I'm going to take this long, and I'm going to exchange it. That is way too fat. Let me try to make it skinnier. There we go. And I'm going to exchange that long into 10 units. 4, 5, 6, 7, 8, 9, 10. Okay? Once I make the exchange, now I have enough to go ahead and take away what I need to take away. So now I'm going to try to take away 6 ones. So I'm going to cross these off. 1, 2, 3, 4, 5, 6. So I take away 6 ones. And so I'm just going to draw down here. What do I have left? So I've got my my flats, my longs, my units. So what do I have left over? I've got 1, 2, 3, 4, 5, 6 units left over. Oh, and you know what? I don't think I counted that right, because I should get 7. 1, 2, 3, 4, 5, 6, 7, 8, 9. You know what? I did one less red one. This is what's nice about using a different color, is because then you know when you make your exchange exactly what you have. So I exchanged one of those longs for 10 units. That looks better. Okay, cool. And then now we can take away, okay, so we took away the 6, and then we're left with 1, 2, 3, 4, 5, 6, 7. Okay, so we're left with 7. And then for the longs, I'm trying to take away 7 tens, which is longs. So I don't have 7 to take away. So I'm going to exchange one of these flats for 10 longs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now that I've made my exchange, I'm going to cross off and I'm going to take away 7 of them. So 1, 2, 3, 4, 5, 6, 7. And I'm left with 1, 2, 3, 4, 5, 6 left over. Okay, and then with my hundreds, I'm trying to take away 100, which is a flat. So I can just cross off this flat, and I end up getting 67. And then in the end, certainly you can do use the standard algorithm. So 243 minus 176. Let's actually work through that and think about what it means when we borrow, and think about how that relates to the picture. So I can't do 6 minus 3. So I have to cross this off, and I put a 1 in front. That's what we learn, right? We're like, okay, we're going to borrow from the one to the left and make that a 3, and then we just put a 1 in front of the 3. Well, why do we put a 1? We put a 1 because we're adding 10. We just exchanged a 10 for 10 ones, and that's why we end up putting the 1 there. So that's what's awesome about the pictures. We kind of see that. So we've got 13 minus 6 is 7, and then we try to do 3 minus 7, and we can't, so we borrow from the left, and we also put a 1 in front of that number, which is essentially just we're adding 10. So 13 minus 7 is 6, and we end up getting 67. Okay, awesome. So this next one, try on your own. So I'm going to draw 312, and then I'm going to try to take away 245. So I'm taking away, I'm just going to write that on the side here so that I can, so I'm going to take away, we're going to take away 200, we're going to take away 4 tens or 4 longs, and we're going to take away 5 ones. So I don't have 5 ones to take away. So I'm going to exchange this, and I'm going to make 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now that I have 10, I can actually take, well, 10 more. I have enough to take away 5. So I'm going to go 1, 2, 3, 4, 5. And then I'm going to try to take away 4 longs. I don't have 4 longs to take away, so I'm going to exchange one of these 10s for 1, 2, 3, or I'm sorry, one of these flats worth 100 for 10 10s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then I'm going to take away 4 of them because we're right here, 245. 1, 2, 3, 4. Okay, and then I want to take 2 hundreds. Well, I have those available, so I'm going to just take away 2 hundreds. And then I'm going to ask myself, well, what is left over? So left over, I don't have any hundreds, so I don't have any. If you want, you could put a 0 there. I've got 1, 2, 3, 4, 5, 6 longs, and then 1, 2, 3, 4, 5, 6, 7 units. So my answer is 67. I just happen to get the same answer as I did for the first one. Totally different problem. So, you know, we did 2 of those, but honestly, it'd be better ideal if you could do, you know, I would say at least probably 5 to 10 of these examples on your own before you really get used to, you know, this process. Okay, so that's blocks. Let's let's talk about some other different types of methods for how to subtract. So the next 3 problems, we're going to do 12 minus 7 equals 5. So it's the same problem. It just shows a different method for how you could do it. So for this first one, it's called the take away concept. You draw 12 of something. So, and in this case, they're postage stamps. You could also use base 10 blocks. You could draw 12 base 10 blocks. 5, 6, 7, 8, 9, 10, 11, 12. You could draw 12 units. Take away, if you're doing 12 minus 7, it means you draw 12, and then you take away 7. 1, 2, 3, 4, 5, 6, 7, and then you're left with 5. So 12 take away 7 is equal to 5. So I would say that that's probably the most popular method for subtraction, and I'm sure you're probably used to this one. Okay, the next one is called the comparison concept. So if you're wanting to do 12 minus 7 equals 5, you could draw 12 of something. So in this picture, we're drawing 12 stamps, and then we draw 7 below. And by comparing, we're just matching these up. We're saying, okay, these are about even. How many more is left over when I'm done comparing? Well, there's 5 left over. So that's another way that you could subtract. And then last but not least, the missing addin concept. So we're going to change it into addition. So 12 minus 7 equals 5. So what you could say to yourself, suppose that you have 7 stamps. So you have 7. but you need 12. How many more stamps do you need in order to complete this and make it to 12? So you start with 7. So if let's say we have the problem 12 minus 7 and we actually don't know what the answer is. So let's say a child is working on this. You would say, okay, well, draw 7 and then ask yourself how many more do you need to add to get to 12. So we're taking subtraction and we're rewriting it to addition. So it's like 7 plus what equals 12. So, and there's plenty of, I've seen lots of worksheets out there that has kids draw this picture and then draw the subtraction and then also draw the addition to go with it. And I think it's a really good practice. All right, so this next part, we're going to talk about estimating and doing some mental calculations. So I love talking about mental calculations with kids because I feel like they can be so helpful in doing math quickly, and sometimes we don't pick up on these methods unless we're told. So I can vividly remember when I was in 3rd grade, we did these mental math challenges where teachers would give us these strategies, and I still remember them and use them today. So one of the strategies is to use what are called compatible numbers, or I've heard some elementary school teachers say friendly numbers. Friendly numbers are like 1 and 9, 2 and 8, 3 and 7, 4 and 6, 5 and 5, because they make 10. And it's not exclusive to those. You can think of things like 11 and 19 if the ends of numbers are 1 and 9, or like 31 and 59. Looking at these two numbers, the 1 and the 9s there, those are friendly, so it makes it a little bit easier to add. So when you have compatible numbers and you're working with addition, remember you can change the order. So like this first one, the 2 and the 8 could go together, the 7 and the 3 could go together and make 10, and then you've got 20. That's way faster than doing 2 plus 7 is 9, plus 18 is 17, plus 3 is 20. Same with this next one. Try to find pairs that are more compatible. So this 2 I know goes with the 8. So 12 and 8 is 20. The 6 and the 4, those are friendly because that makes 10. But then we've got this 1 and 1, which is 20. So altogether that's 30. So we've got 30 and 20 is 50. That's a lot faster than adding left to right. This next one, you can see this 1 and the 9 there. So those numbers are friendly. 20, so 1 and 9 is 10, and the 2 and 2 is 4. So 40 and 10 is 50, plus 25 is 75. Okay. This next one is a little bit harder. So this is called equal differences. There's a couple of different ways to write it. I actually prefer doing it a little bit different than how the book shows how, but either one works. So when you're doing equal differences, when you're subtracting like 22 minus 8, and I always say this to my kids, like if the subtraction is hard, change the number in some way to make it easier, and then in the end you can modify it to so that your change didn't affect the answer. So for example, 22 minus 8. One thing you could do is you could say, you know what, instead of 8, I'm just going to take off, whoops, not 8. Instead of minusing 8, I'm going to take off 10 because that's easier. I know 22 minus 10 is 12. Whereas minusing 8 would take a little bit more brain power, but I took away too much. How much more did you take away than you should have? Well, I took away too many. So I took away too many. Too many. So to compensate, I'm going to add 2 to my answer and get 14. So 22 minus 8 is 14, but in your head you could say, you know what, I'm going to subtract 10 and get 12 and then add 2 back so that I basically fix my adjustment. Same thing here. So 35, instead of minus 9, I could just do minus 10 and get 25 because that's easier. Well, I took away 1 too many, so I'm going to add 1 back. So 25 plus 1 is 26. Now, if this doesn't make sense, another way you could think of it is you could add 1 here. Okay, so that makes 10, and you could add 1 there. So 36 minus 10 equals 26. So you're doing the same thing to both numbers. Add 1, and then you end up getting the same answer that way too. So whichever way makes more sense to you is totally fine. This one, you know, minusing 199, that takes so much brain power. So don't subtract 199. I'm going to do 894 minus 200, because then I can just do 8 minus 2 and get 694. Way easier. But I subtracted too much. How much more did I subtract than I should have? Well, I subtracted 1 too many. So if I took away 1 too many, then I'm just going to add 1 back and get 695. Okay. So just some strategy to help us add faster or subtract faster. All right, so this next one, you might have seen, I'm sure you've seen people do this at the grocery store or any store. When you give people money and they're counting back your change, a lot of times they will add up to what you gave them. So if you gave them a $20 bill and they gave you change, then they'll be adding up to make the 20. So essentially what you're going to do is for 55 minus 20 is you're going to say, okay, I'm going to start at 20 and I'm going to count up to 55. So, and you can count by tens or fives or however you like to count. So, and I do this with my kids all the time. I'm like, okay, you can't hold all this in your head. So let's start at 20 and let's count as close as we can get to 55. So I'm going to say 20, 30, 40, 50, 5. That's how I would count in my head. And then you ask yourself, well, what did you count? You added 35 more. And you could certainly just use your fingers as you're counting. So the answer 55 minus 20 is 35. 400 minus 185. Start with the 185 and then add up to get to the 400. So I'm going to add 15 to make 200. And then I'm going to add another 100 and then another 100 to make 400. So I've got 15, 100, 200. So 215. And the key here, you know, when you're doing this in your head, you're not writing all of this down. So the reason that I'm writing it down is so that you can see my thought process. But in reality, we're just teaching kids how to do this in their heads. I wouldn't require students to necessarily write this down if they didn't, if they were doing it in their head. So with this one, I'm going to start at 50, 135 minus 50, and then I'm going to work up to 135. So if I add 50, that gets me to 100. And then if I add 35, that gets me to 135. Well, what's 50 plus 35? 5 and 3 is 8. 85, I can do that in my head. If that's too much to do in the head, you didn't have to do the 35. You could have, there's lots of options here. You could have said plus 50 is 100, plus 10 is 110, 120, 130, 135. So that would have given you the same answer too. Alrighty, so we're getting to the end here. So last page. So we're going to talk about approximation. So what we just did was not approximation. What we did, we got exact answers on that last page. We just used some tricks to get there. This page, we're going to talk about rounding so that we can make our mental math easier. So like if you're at the store and you want to just estimate the cost of something and you don't need it to be the exact answer, these strategies could be helpful. Estimating is a really important strategy in elementary school because it allows those students to really just kind of have a greater understanding of numbers in general and have a better number sense. So this first method, we're going to do a couple different methods. And you have to pay attention to the directions. So like in the homework, if it says estimate, that means you're not going to get the exact answer anytime you see that word. You're not going to get the exact answer. It says to round each number to the place value of the leading digit. So this means we're going to use rounding rules. This means that if it's greater than or equal to 5, we're going to increase the number. If the number to the right is less than 5, then we're going to keep it the same. So we're going to look at the leading digits. So 624. 624 is closer to 600. So this 2 tells us to leave the 6 alone. Minus 289 rounds to 300 because this 8 tells us to increase the 2 to a 3. Minus 132 is closest to, not 130, it's closest to 100. So we're rounding in this case to the nearest hundredth place, but it just depends on the type of number. You always just want to round to the leading digit. So 600 minus 300 is 300, minus 100 is 200, and I'm going to use my squiggly equal sign to mean approximately. So with this one, we're going to round, I'm just going to circle those leading place values. So 4723 rounds, it's closer to 5,000, plus 419 rounds to 400, plus 1040 rounds to 1,000, and then we'll add those together. So it looks like we've got 6,400, and that's approximately. And then last but not least, we're going to round this to 800, and then 200, and that gives us 600, and that's also approximate. Okay. So this next one, we're going to combine a strategy we used on the last page, compatible numbers. So these are those friendly numbers. So think 1 and 9, 2 and 8, 3 and 7, 4 and 6, 5 and 5. And we're going to also round. So approximation. If you see the words approximation in the instructions, that means you're allowed to round. So this next problem, what you want to do is find numbers that are close to being compatible or friendly numbers. So when I look at this, I see this 33 and 71, and this looks awfully like 30 and 70. So those are about 100. The 54 and 52, that's about 100 too, because these are about 50 and 50. And so that's about 200. And then it asks, without computing actual answer, predict whether your approximation is too small or too big. Well, I rounded all of these numbers down, so I'm going to say that this is too small because I rounded my individual numbers down. Next one. So let's look at the next one. Maybe I put the 88 and the 24. That's about 80 and 20 is 100. And this is almost 40 and almost 60, and that's 100. This is also about 200 when we add those together. Okay. Now this one, let's see, it looks like the 88 I rounded down, and the 66 I rounded down, and the 24 I rounded down. The 37 was the only one I rounded up. So I'm going to say that this is also too small since most of the numbers I rounded down. Okay, last but not least, front-end approximation. So this is a really simple way to round. I would say that this rounding method is probably the least accurate of all of them, but it's a really great way for younger students to start rounding because the rules are super simple. So all you have to do is you keep the leading digit and you make the rest zeros. This is different than what we did above. So up above, I circled the leading digits, but we used our rounding rule. So in some cases, like 289, we rounded up to 300. Down here, we're just going to keep the leading digits. So if it's a 1, this becomes 1,000. This number becomes 7,000. And this number becomes 3,000. And we add those all together. So we've got, those are friendly numbers. So that would be 10,000 and then another 1,000. So 11,000 approximately. For this one, the 47, we're just going to keep the 4. Now, if we use the rules above, it'd be a 5,000, but we're not. We're just going to, front-end approximation says just leave the leading digit. The rest is zeros. Subtract 1,000, and we get about 3,000. And then this one, I'm going to start with the biggest number so I can put them vertically. So we're going to say 4,000 plus 500 plus 700, and I'm going to add those all up. Okay, and then last but not least, we've got 7,000 minus 500 gives us 6,500. All right, so as always, let me know if you have any questions. Next up, we're going to do some multiplication and division.